So in this video, we're going to find the antiderivative of 2 over square root of 16 plus 25x squared. It's going to be a trig substitution, and I know you're going to use tangent because of the x squared plus a squared nature. Now when I do this, though, I'm going to need it to be more than just tangent theta, because I need to get rid of that 25, so when I square it, well, when I square 5, that's going to cancel out that 25. And when I square 4, that's going to be the same as the 16. So that's how I picked the 4 and the 5. So my dx then is 4/5 secant squared theta d theta. Always calculate your dx right away, because otherwise it does tend to get forgotten. Let's sub everything in and see where we're at. So subbing in my dx, I've got 2 times 4/5 secant squared theta d theta on top. And on bottom, I've got the square root of 16 plus 25 times 4/5 tangent of theta, that quantity squared. Again, having that 4/5 there is going to help us get a whole bunch of stuff to cancel. I'm going to start pulling constants out. So 2 times 4/5 is 8/5. And that would leave just the secant squared theta on top, d theta. On bottom, when this gets, well, let's go ahead and write this out. 16 plus 25 times 16 25ths, so I'm squaring this term, tangent squared theta. Those cancel. Oops, I forgot my radical. Let's do that. Those will cancel, and now I can pull a 16 out, and I can even pull that out of the radical. So what that's going to look like is 8/5. Top we're not touching just yet, secant squared theta d theta, over 4 times the square root of 1 plus tangent squared theta. The reason we can do that, again, we're factoring out a 16, and then because it's a product, we can pull the 16 out of the radical. Square root of 16 is 4. That's going to contribute to my constant out front. So that's going to give me 8 over 20, which reduces down to, because we can just cancel here, a 2/5 out front. We have a secant squared theta on top, d theta. And then by our Pythagorean identity, 1 plus tangent squared theta is equal to secant squared theta. So on bottom, we end up with square root of secant squared theta. This is going to simplify pretty nice, because secant squared theta, this is just going to be secant theta. This simplifies all the way down to secant theta d theta. Now the antiderivative of secant theta I'm not going to do here. I've done it in another video, and you can check it out. But the antiderivative is natural log of the absolute value of secant theta plus tangent theta plus c. But I'm going to put a 1 on that c, and you're going to see why as I go to simplify this to match up with integral tables. Now, we need to know what tangent theta and secant theta are, though, in terms of x. Tangent theta we already have. I just need to solve this for tangent theta. So that tells me that tangent theta, cross multiply here, equals 5x over 4. And I'm going to use that to find secant theta. And I like using a right triangle method. Call this guy, for instance, theta. That means the opposite side is 5x, the adjacent side is 4. By the Pythagorean theorem, this side here is a squared plus b squared, square root of a squared plus b squared, so 16 plus 25x squared, which probably looks pretty familiar from our original. That means secant of theta, which is hypotenuse over adjacent, is square root of 16 plus 25x squared over 4. So we can get this thing back in terms of x. So we have 2/5 natural log of secant theta, which is square root of 16 plus 25x squared over 4 plus 5x over 4 plus c1. Now, I think this is fine for a complete answer. It's a nice antiderivative, but it may not match with what you see in your integral tables. So we're going to do a little bit more work on this one, just to get it in the form that an integral table would have it. So if we move this up, what I'm going to do is, under this radical, I am going to factor out a 25. So I have square root of 25 times 16 over 25. Shouldn't have a parenthesis there. Let me give a little more space. 2/5. Natural log. I'm going to factor the 25 out of here again. Sorry about the mistake. Square root. So I factor out the 25. That means I'm dividing both these terms by 25. That first term then becomes 16 over 25. The second term just becomes x squared all over 4 plus, and I'm just going to rewrite this as 5/4 times x, and you'll see why shortly. Okay, so all I did was factor a 25 out of that first term. Well, now I can split my radical up over each part of the product, and so square root of 25 is 5. So I get 2/5 natural log of the absolute value of 5, and I'm just going to write this as 5/4 times square root of 16 over 25 plus x squared, because I don't want a fraction in a fraction, plus 5/4 times x plus c1. Now, notice I've got a 5/4 in each term. So 2/5 natural log, I'm going to rewrite this as square root of 16 over 25 plus x squared plus plus x, and those get multiplied by the 5/4 plus c1. Now, by properties of logs, because I've got a product inside the log, I can write that as the sum of two separate logs. So natural log of the absolute value of square root of 16 over 25 plus x squared plus x, that ends that natural log, plus 2/5 from this 2/5 out front, natural log of 5/4 plus c1. Well, here's what happens in the table and why you don't see this part here. This part here is just a constant. So we absorb it into another constant that we call c. That'll get taken care of when we have an initial condition. And so the final answer you might get from a table of integrals will look a lot more like this. 16/25 plus x squared plus x. You might see the order reversed on those, plus c. So we did a little simplification at the end. It's not really necessary for finding the antiderivative. We were correct back at this answer. But if you wanted to match it up with a table of integrals, that's how we could do it.